Okay, let's just continue with this. From here, we need to compute the subproblem cost vector. So you need to compute WA minus C. That's the cost vector that you use for your subproblem. In this case, W is 0, so this part is simply 0. So this gives you minus C. I think God tells me to stop here. Okay. So minus C is, this is the problem then that you solve. Maximization of WA minus C times X, X in X. That's the subproblem defined by the current W and alpha. And this problem, of course, becomes the following. You maximize, because this part is 0, you maximize minus Cx, which tells you that you're maximizing 2x1 plus x2 plus x3 minus x4. Subject to x1 less than or equal to 2, x1 plus x2 less than or equal to 3, 2x2, sorry. x1 plus 2x2 less than or equal to 3. And then minus x3 plus x4 less than or equal to 2. And what is the last one? 2x3 plus x4 less than or equal to 6. With x1, x2, x3, x4, non-negative. Of course, this splits into two subproblems.
This 3 is going to be 5.
Say that again.
Second constraint, right-hand side, will be 5.
This is 5.
Second one, not.
What was this? 2? 2. But I have 6 here.
2, 5, İlk ikisi.
This one.
Yes.
Okay. 2, 5, 2, 6, right? Okay, thank you. It took a while to get to the right point. But anyway. All right, so this problem splits into two subproblems. Subproblems 1, subproblem number 2. Subproblem number 1 involves x1 and x2 variables. The other one involves x3 and x4 variables. Because the constraints just decompose. There's nothing that couples x1, x2 to x3, x4. You're simply maximizing 2x1 plus x2, where x1 and x2 are taken from the first feasible set, capital X1. And the second subproblem, you're maximizing x3 minus x4, where the two variables come from x2. Okay. By inspection, the optimum solution for this one is where? 2x1 plus 2, 1. You're maximizing, so I guess that should be the optimum, right? 2 and 3/2. That's your first optimum. What about the second one? It's 1 minus 1, 1 minus 1. So you have going like this. 3, 0 should be the optimum, right? Yeah. That should be the optimum. Let me just check this one. Yeah, it's correct. So the extreme point we have is Yeah. The x bar solution that we have, or let me call it x2. I already used x1 for the initiating one. So let's just call it x2. x2 is the composition of these two. That's your x2. And you need to compute R2 and see if that one is positive or not. R2 is the, this will introduce lambda 2 into the objective function if R2 turns out to be positive. Okay? So how much is R2? You just evaluate the objective function. 2 times 2, which is 4, plus 3 halves, plus x3, which is 3, plus or minus 0. How much is this? 7, 8.5, or 17 over 2. It is positive, so lambda 2 enters because it's positive. Now I need to compute y2, which is going to be your B inverse times AX2 times, or AX21. Okay, that's the column. What is AX2? Let's first compute that. A is what? It's what you see there, 1101. Long computations, huh? 1002. This is your A matrix. Times x2, which is what you've got here. What is the output of this? I'm too lazy to compute that. It happens to be 5 and 7 halves. So this is your A2 cap. That's what it is. A times the second extreme point. Okay. All right. So B inverse or Y2 is going to be B inverse, which is the identity, times this thing, which gives you the same thing, of course. And now we write this next to the tableau. So I'm going back to my old tableau now. We write it here. That's your lambda 2, which you want to enter. And your R2 is 17 over 2. This is the initiating tableau. This is the entering column. What was this? 5 and 7 over 2. Okay? And then you look at your ratios. There's something wrong here. Oh, there's a 1. I forgot. There's a 1. Yeah, sorry. Okay. There's a 1 here. So let's revise this. Yeah. There's a 1 here, which I forgot. So you should be multiplying this one with this. Okay, sorry. Please don't make the same type of mistake that I make on the board. So B inverse times, of course, you need 3 entries here. And the last one is always a 1. And that's what you got. Yeah. All right, what is the minimum ratio here? I pivoted on this one, so that should be the minimum ratio. 2 over 5, 3 over that, 1 over 1. Yeah, that's so S1 exits. Okay. And then you pivot to get the new tableau. So I'm not using the product form of the inverse here. We're just using pivoting. Okay? What are the basic variables? S2 and lambda 1, they used to be basic, they are still basic. And lambda 2 is the new basic. Okay, so that's the new solution. Now the reduced cost for the first slack, which is the non-basic variable now, is equal to minus 17 over 10. And since it's less than 0, you don't enter that particular one. It just exited, so obviously it will not enter again. Not at this point, at least. So you need to solve the subproblem again. To do that, you need to compute WA minus C vector again. In this case, of course, it will be a bit different. Minus 17 over 10, 0, 0. No, just 0. Times 1, 1, 0, 1, 1, 0, 0, 2, minus C. Minus, what is the C vector? I have minus 2, minus 1, plus 1. That's the C vector from the original problem. And the output of this happens to be 3/10, 1, minus 7 over 10, and minus 1. That's your cost vector for the subproblem solution. Again, you decompose into subproblems 1 and 2, where the first one involves 3 over 10, x1 plus x2, where x1, x2 come from the first feasible set. The second subproblem, you maximize minus 7/10 x3 plus or minus x4, subject to the constraints of the original problem that defines x2. All right, so when you solve, by the way, of course, when you solve these things, you must also add alpha. Don't forget that, okay? In the first case, alpha was 0, so we did not add it. In this case, alpha is still 0. This is always alpha here. Alpha is still 0, so we're not going to add it. But if it turns out that it's a non-zero number, you should always remember to add that. Otherwise, you know, you may arrive at a wrong conclusion. Okay, so the solution here happens to be 0, 5 halves. And the other one gives you a solution of, what is it? 0, 0. So, combining these two, my third extreme point is 0, 5 over 2, 0, 0. Now I need to compute y3, as well as, you know, the reduced cost for that. Let's just compute the reduced cost first. What is R3? The objective value you would get from here plus alpha. What is the objective value you would get here? 3/10, 0, 5 halves, so it's 5 halves. Okay. Now I need y2 which is my B inverse times A, not Y2, Y3. Y3, which is A, B inverse times AX3 and 1. B inverse is what you see up there, 1/5 minus 7/10 minus 1/5, 0, 1, 0, 0, 0, 1 times AX3. Well, you can compute AX3. It turns out 0 and 5/2. And then you have, of course, A1 here. That's your AX3, okay? And when you compute this, you get 0.5 over, well, you get the same thing, yeah. Do we get the same thing, or did I make a mistake here? The first one is 0, the second one, yeah, because this is 0, it doesn't, you know, the bad column does not affect the computation. Okay. So where do we write this? God, this is, you know, a little bit confusing. I write it here, right? This is my lambda 3 that's entering, and my 3 is 0, 5 over 2, and 1. The reduced cost happens to be 5 over 2. You look at the ratios, and this is the pivot element at the end of the ratio test. So who exits? Lambda 1 exits. That's what I have. I used to have a teacher who just stood on the in front of what he writes down, so we could never write it down. I had to do the same thing because there's no place to go for here. Okay. So we compute WA minus C. WA in this case is minus 6 over 5 and 0 times the A matrix, which you can fill in. And it's going to give you minus C. Okay, so the result of this is 4/5, 1, minus 1/5, and minus 1. This part gives the objective function of the first subproblem. This part gives the objective function of the second subproblem. And then you solve over the appropriate feasible sets. It turns out that optimum for this happens to be at 2 3/2, and the optimum for the second subproblem happens to be at 0, 0. So x4, the fourth extreme point, is just 2 3/2, 0, 0. And R4 happens to be, how much is it? Well, you just compute it. Using the objective function coefficients times the x4 plus alpha. And when you perform this multiplication out, how much is alpha here? It's -5/2. Okay, so don't forget that. The final result comes out as 3/5. Don't forget your alpha, please, please. You know, a lot of people make that mistake, so extra attention for that. And then you compute y4, which is b inverse times ax4 and 1. And I'm just going to give you the result directly. 2/5, 3/5, and 3/5. That's your y4. So you go back to your tableau. By the way, what are the basic variables here in this tableau? We pivoted on this one, so lambda1 is replaced by lambda3. That's the last basic variable. The other ones are lambda2 and s2. Okay, so here we've got lambda4 now. The reduced cost is, what was it? 3/5? Where was it? 3/5. I wrote it somewhere, but I forgot now. No, it's not 3/5. It's 5/2. The reduced cost is 5/2. Where did I write it down? Oh, okay, here. How come there's something wrong here? Just a second. Well, I either made a copying mistake or I made a computation mistake. Either one. Because I've got 5/2 here. Let me see if I'm looking at it. No, I'm not looking at the right tableau. This is a copying mistake. Yeah, this is 3/5. Sorry. Okay. And then we have 2/5, 3/5, and 3/5. You look at the ratios. That is the pivoting element at the end. And then you pivot and it gives you lambda2, lambda4, lambda3 as your basic variables. You've got 1/3, minus 1/3, 0, minus 2/3, 5/3, minus 1, 5/3, minus 25/6, 7/2, 1/3, 1/6, 1/2, minus 1, minus 1, 0, minus 5. That's the new one. You compute WA minus C, which gives you 0, 0, 0, minus 3. This part gives you an optimal solution of 0, 0. This part gives you an optimal solution of 0, 0. So the extreme point you have, it's not x5, but rather it's x1. We're back to the initial extreme point that we began with, which was this one, the origin. Okay? So lambda1 enters again. Long process, but it's a possibility. Lambda 1 enters if, of course, R1 happens to be positive, so you need to compute R1. R1 is the objective function value of this. How much is it? Well, it's going to be the objective function value plus alpha. Is alpha 0 here? Yeah, it is 0. So it is actually, this is also 0. So it's 0, which means that all the reduced costs are less than or equal to 0. So we stop. The optimal solution is what we have in the final solution. Last basic feasible solution in the master problem is optimal. So what is the last basic feasible solution? It's this one. Lambda 2 is equal to, what is it, 2/5? Lambda, where am I? Lambda 4, sorry, it's going to be 1/3. I'm looking at the wrong one. Lambda 2 equals 1/3, lambda 4 equals 1/6, lambda 3 equals 1/2. All the rest of the lambdas are 0. So your actual optimal solution to the original problem is a convex combination of the extreme points corresponding to these lambdas. It's going to be 1/3 times x2 plus 1/6 times x4 plus 1/2 times x3. So 1/3 times, what is x2? I've got 2, 3/2, 3, 0. Plus 1/6 times x4, which happens to be 2, 3/2, 0, 0. And 1/2 times x3, which happens to be 0, 5/2, 0, 0. I hope I did not make a printing mistake here, because I'm not too good with copying numbers. Theory is pretty good. Copying numbers, I'm not very good with that. That I leave it to students, but then of course I have to do it here myself. So what is the result of this? I don't know. I get 1/7/4, 1 and 0. That's what I have. That's your solution to the original problem. Looks like a long process, but actually for large problems this is an efficient method, if you know how to implement it, of course. Okay? Okay, we still have some time, so take a deep breathe, take a deep breath, and then be ready for more to come, okay? So, here's the problem we're dealing with. Now we no longer assume x is bounded. We have to deal with that and see what happens. Let's just take the case with equalities again. And this is again special structured in most cases. However, I should probably tell you that it doesn't have to be special structured. But the main advantage comes from the fact that if this is a special structured polyhedral set, then the subproblems are easy to solve. Okay, that defines the subproblem. But it's not necessarily bounded. So we assume x1 through xt are the extreme points of x, and let's just assume d1 through, say, dl are the extreme directions of x. So now you also have directions. So you can represent any x in x as a convex combination of the extreme points plus a non-negative combination of the extreme directions. So we are going to have x equals lambda j xj going from 1 to t plus, say, mu j or mu I di I going from 1 to L, with the additional requirement lambda j's adding up to 1 and lambdas and mu's are all non-negative. There's no additional requirement on mu other than non-negativity. So rewrite the original problem in the form minimization of c times this representation, which gives you, what does it give you if you simplify? It will be cx, which is expressed in this way. So it will be cxj times lambda j, j going from 1 to t, plus c times mu I, di, c times di times mu I going from 1 to, say, L. Okay? That's your objective function if you just substitute what you see here for x. Subject to the constraints. Again, you substitute for x the expression that you have here. And that will give you a times xj times lambda j, j going from 1 to t, plus a times di mu I going from 1 to L equals b. That's what you will get. Plus, you have lambda j's adding up to 1. And then finally you have lambda and mu as vectors non-negative. Okay? How many here? M. How many? 1. So again, you needed m plus 1 basis. This is the master problem, by the way. All right, so suppose given a basis B with W and alpha defined by, what is it? CB cap B inverse, where CB cap is, so if you look at these as CJ cap, what is it? Well, let's just write it this way. yeah, okay. CB cap B inverse, where CB cap has the costs C times xj and C times di for basic lambda j's and mu i's. Okay? So it's got the appropriate cost values in it. So you've got the revised simplex tableau, W alpha here, Z bar here, B bar here, B inverse here. What is B bar? B inverse times BM1. What is this? CB cap times B bar. Okay? Same old stuff. All right, so what am I supposed to do? I need to compute my reduced costs. So to do that, let's look at the reduced cost for the jth lambda, lambda j. It has W alpha times the column A, xj, and 1 minus Cj cap, which is C times xj. Okay, that's your reduced cost for lambda j, which simplifies to Wa minus C times xj plus alpha. Nothing different from the old one. Now the reduced cost for the mu I is, it's a little bit different, because this time you've got the column ADI with a 0 at the end tagged, okay, rather than a 1, minus C times DI, which gives you WA minus C DI. So you have no alpha in this case. And you're looking for the maximum of these reduced costs of the two kinds. Okay? So looking for the maximum of them amounts to solving this subproblem with, what is it, x, where x is restricted to capital X. Now I'm going to add alpha here. Which is actually in the first type of reduced cost, but it's not in the second type. Nevertheless, this maximization is not really affected by alpha. So let's get to the conclusions here. So this is the subproblem, W alpha. If the subproblem has an unbounded solution, this problem could have an unbounded solution. Okay? Then it can be caused only by one of these extreme directions. Then an extreme direction, say dk, is discovered with reduced cost R mu k defined by WA minus C times dk, which happens to price out as positive. Okay? So you have an entering variable entering mu, but the column underneath it is all non-positive, so there's no ratio to test for, so it's unbounded. Okay? In this case, we enter mu k with reduced cost r mu k with column, or with yk defined by b inverse times a dk and 0. Okay, so you compute this, you take your reduced cost, you put it next to your tableau, you just compute this stuff, and then you look at your ratios. Now, the fact that you have an unbounded solution in the subproblem doesn't mean you have unboundedness here, okay? They are two different things. It tells you what to enter. It tells you that one of the mu's must enter. So you enter that, you look at your ratios, and then you do your pivoting operations and whatever. You get the new solution to the optimal, to the master problem, okay? All right. Now, the second case is when this is not the case. So, if the subproblem defined by W alpha is not unbounded, then we have a solution, say x bar, which is an extreme point of x, with reduced cost, say r bar, which happens to be WA minus C times x bar plus alpha. That's the solution, okay? If r bar is less than or equal to 0, then lambdas as well as mu's, they don't price out favorably, so nothing enters, which means you're done. The current basic feasible solution to the master problem is optimal. There's no mu which prices out favorably because it's not unbounded. The reduced cost, the best reduced cost, is also less than or equal to 0, so there's nothing to enter. If, on the other hand, r bar is positive, then x bar or lambda bar associated with x bar enters. Compute. R bar is already computed, so we also compute y bar, which is your b inverse times a x bar 1, and then write it next to the tableau. Which had W alpha, Z bar, B bar, and B inverse. So you write it here. In this case, lambda bar enters, or lambda k, whatever you want to call it. Y bar here, R bar here, and then just proceed with your regular ratio test and so forth. Okay? So I'm not going to, the rest is straightforward stuff. Identify the exiting variable. Then update using either pivoting or product form, whatever. So you get the new tableau either via pivoting or via product form of the inverse. Apparently, product form of the inverse gives you a lot of trouble, as far as I can tell from the exam papers. So use pivoting. Okay. Many people made many mistakes. Some people, they just didn't even attempt, you know, which is fine with me. But, you know, it's computationally a better way of handling things. Anyway, this is really easy stuff. Unfortunately, we're out of time now. Or maybe fortunately, huh? I was going to give you an example, but we don't have time. So next time on Wednesday, I'm going to start probably talking about minimum cost network flow problems, which is a new chapter in your book. The example for this, Hatice may work out a smaller, well, I have an example, so she can just work that out maybe in the second period, okay? All right, that's it for today.